So welcome again. We are continuing today the presentation of some topics that we will be covering during the lecture, and I will do this through some videos. We will comment the videos, and please, if you have any question, any doubt, or you would like to understand a bit more, just pose your question. Okay, I'm here for this reason. So we have already seen some videos concerning kinematic redundancy and how we can handle these extra degrees of freedom in order to control in an optimal way the robot and satisfy some additional criterion. Then we have seen some data on what we have called identification of the dynamic coefficient within the robot model. So with some plots that show how good is this identification and what should we do for obtaining this model. Now we will move on, presenting more videos on interaction with the environment, so force and motion control simultaneously. Also on pure motion control, and in particular, I would like to show you some issue related to the fact that we assume that the robot is rigid, fully rigid, so it means rigid links, which is a very reasonable assumption, and also rigid transmission, which is not always the case. So what happens in the presence of joint flexibility, or, and this is a kind of a parasitic effect, or what happens when we have joints which have a stiffness, finite, but variable on demand. So there is a second actuator that provides the change of stiffness of the joints, from very rigid to very soft. Okay? And what are the use of this new class of variable stiffness actuation of robots? And finally, a few videos that handles the problem of coexistence, safe coexistence between humans and robots that share their workspace, how they can interact physically, and how they can collaborate by exchanging, in a controlled way, forces. So let's start with the first two videos. These are quite old videos, actually from the mid of the 1990s, and they are collected in the Springer Handbook of Robotics, which is a main publication. There's a second edition of this handbook. There are 300 contributors worldwide, and myself and other professors of this department contribute in several parts of this handbook. And there's a nice addition, the multimedia, in the second edition. So a collection of historical or even more recent videos that are support the presentation in the chapters. So I've taken this to be actually one video, and then I made two clips from this work that was performed at the University of the Katholieke University Leuven in Belgium by the group of Joris de Schutter and colleagues. So here you can see a standard industrial robot. This should be a KUKA, in fact, 6 degrees of freedom. It has also an end effector, which is both compliance and through which forces are measured at the level of the tool. So in the first video, we have a problem of contour following. So we have a mechanical object. We would like to follow the contour while applying forces. Okay? And this contour may be known in advance. For instance, if you have a CAD model of the part, and you want to, let's say, do some debarring tasks, so you want to eliminate geometric parts that are out of the nominal surface, or may be acquired through vision. So you may have a camera overlooking the object, and so you can extract the geometric information of where the end effector should move while applying forces. We already discussed this issue, and we mentioned that in general you need to have some dynamic model in order to understand how to control the joints of the robot. If you have a force torque sensor, you can slightly get rid of this, but we will see the full formulation in the hybrid force velocity control topic. Finally, you may not know anything from the object, so you would like to identify online the geometric part, because you need to identify this part, because more or less what you're doing, so if you have a surface like this, and you are here, and you don't know where to go, in fact, so you need to identify that there's a tangent to the surface and a normal to the surface. On the tangent you control velocity, and on the normal you control the force. And this is what happened here. But you don't have this frame, so while moving in contact and applying some force, otherwise you may detach, you have also to rotate the frame in such a way that you know where the normal is. And you can process your data in order to do so. So you do a kind of learning. In fact, it's a recursive identification of geometric parameters while following the surface. Let's see what happens. In this case, the tool is equipped just with a roller, so there's no action, no elimination of material, but it should stay in contact with enough force so that the tip, you will see a close-up view, can roll on the surface itself. Initially, you move quite slowly. In this first video, in fact, there is no information on geometry. This is why, while exploring this part, the robot needs to move slowly. Here you see the CAD information, so many frames that can be attached to the geometry, or you could have a visual information, or you can do this learning like before. And of course, if you combine this information, then you can repeat the task at a much faster speed with the same performance. Okay? So this is a classical control problem of the interaction. So you have to move in certain feasible direction and at the same time exert some forces. Now the second piece of let's say video clip is a classical assembly task. It's the peg in a hole problem. It's not that in industry they want to put pegs in holes, but in fact this is a paradigmatic example of an assembly task where you have to insert part into other part in order to get the full object. And in order to do an assembly, you need to exert forces as well. So here the situation is rather general. We will see first part of the video where the insertion is prepared in the sense that the peg, which is held by the gripper of the robot, is on this surface. In the surface there is a hole, so he will explore, the robot will explore the surface until feel some variation in the contact force. It will engage in the hole initially with a 3-point contact and then modify the orientation of the peg so that the insertion can be completed. And in the last part there will be more complete strategy. So the robot starts out of contact, will search the contact with the surface. It has a model of this surface, of course, so it has to understand where the contact occurs, and then it will explore the part until it finds the hole and does the insertion as before. So let's see this insertion strategy. It's model-based insertion because you model the type of contact that may occur. So here the robot goes in contact. There's a 1-point contact at this point of the extreme of the bottom part of the peg, and now it gets into the hole, and in this situation there are 3-point contacts, 2 on the side and 1 on the back. You can model this by virtual joints because in this situation you can move only in some prescribed condition because you have a geometric constraint imposed on the object, and the object is more or less rigidly held by the robot, and then you can complete the things. And here you see again the full strategy. First get in contact, then follow the surface, get up, be on the surface, and now again you are in the same situation as before, and you can complete the insertion. Any question on this? Now, I have a question for you, and I would like somebody to reply. Do we really need a force sensor here? Or we could do this just by position control? What do you think? Any idea? Well, if you remember, we mentioned when dealing with components of robots, we mentioned the existence of a device which is similar to a force torque sensor mounted on the end effector, which is called the remote center of compliance, which is an object that is mounted on as an end effector of the robot and can accommodate in a passive way forces arising from the contact with the environment, so that the robot does not know anything about contact or not. It's programmed to move in a certain way, and the small errors that you may get, for instance, in the insertion of a peg in a hole, are compensated passively by this device, which consists of a number of springs that will move the bottom plate of the RCC device with respect to the top plate, which is bolt on the end effector of the robot. So the robot does the motion, the programmed motion without caring, and the passive things does the job. So it means that such assembly can be done also with pure position control, provided that you include some compliance in the structure. And the typical way is using such an RCC device. Even the gripper of the Leuven setup has some compliance. If you notice, the peg was vibrating a little bit. Of course, once you introduce this passive compliance, so a form of springs that are not controlled, you may induce some vibration. And so you reduce the accuracy, especially if you're going fast. So there are pros and cons in this. Whereas, if you have a force torque sensor, you can be very stiff, measuring forces, and reason about the set of data to understand what is the next motion in order to complete the task. Okay? So remember, there are always alternatives, more sensing, less sensing, more information about the model, less information about the model, and so on. Okay, the next two videos are related with motion control, in particular in the presence of elasticity in the transmission. What you see here is the ancestor of the KUKA lightweight robot. In fact, this is still the DLR-3 lightweight manipulator that developed then into the KUKA-4 research manipulator, and later on KUKA produced an industrial version, and in fact it changes also the name a little bit, the shape, and it's the current KUKA AIVA lightweight manipulator, which is very successful in selling, especially for collaboration tasks, where you have a human in the vicinity of the robot. Why is that? Because this is a lightweight robot. The full weight of this was 14 kilograms. At that time, the research version could hold the same weight as a payload. So there was a 1-to-1 ratio between payload and own weight of the robot, which is completely different from industrial robot. As you know, a typical industrial robot may weigh 120, 150 kilograms and have a payload of, let's say, 3 to 5 kilograms. Okay? And the reason for this is because in order to achieve accuracy, it should be very stiff, the structure, so very massive, so that vibration never occurs, and this is being paid by a heavier total mass in motion. Okay, so in this case, we have a lightweight structure. The links are originally were made of fiberglass, later on aluminium, but they are sufficiently stiff, so the links do not bend. But internally, in order to achieve high torques on the motor side by using small motors, so that to reduce the weight of the motors in the total system, they use harmonic drives. You remember what are harmonic drives? So transmission elements which are able to do online in a compact way amplification of torques by a factor of 160 up to 200 with less loss of energy, so quite efficient, but they introduce some compliance because the flex spline internal to the harmonic drives has some compliance. Now, compliance on one joint, on the second joint, on the third, up to the seventh joint, if you sum all of them together, you will have a situation like the one on the left, where the robot is commanded to stay in position. So, the current position is the target. The motor are braked in that position, or you can use high positional gain so that you don't move from there. Still, especially if you add a payload and you give a perturbation, if the system was completely stiff, it would not move. On the other hand, you see this type of vibration. Okay? And the vibration are just because you have fixed one part, the motor, you have some elasticity, let's say a spring, and you're pushing another mass at the end effector level, and what you see is not the motion of the motor, which stay fixed, but the oscillation due to the compliance of the transmission. Okay? So this is good and bad, again. Sometimes you introduce intentionally compliance if you're able to control this vibration so that the system may absorb energy, especially if it goes in contact. Now, the second video here is, in fact, another type of interaction. It's both motion and force control. So again, in this simple case, the robot should not move, but it will react to the application of an external force, which is not measured, by the way, but it will react like a mass spring damper. So like you have a mass with a spring and a damping device that dissipate energy, and you're applying a force, this mass will start to oscillate and then stop. And of course, the higher the mass, the lower will be the frequency of oscillation. The stiffer is the spring through which this mass is anchored to the ground, the less will be the amplitude of the oscillation, and the larger is the damping that you introduce, the faster the oscillation will vanish. Okay? So you have parameters in the control law to choose, and this is a very common practice. This is what is called impedance control, and in particular here you will see that this scheme has been made selective with respect to direction. The only condition in this experiment is that the human or the environment was pushing close to the end effector, so that we can imagine that this impedance model is applied at the level of the Cartesian endpoint of the robot. And this is what happens if he pushes. He reacts without oscillating in this direction, but if you push in the other direction, you see that much more oscillation because of the gains of the parameters in the impedance controller, which are selective in the Cartesian direction. Okay? The other things that you may have seen, let's see if I can run this again, yes, is you can also fix the end effector position and orientation, like in this condition, and now you can move around the structure without changing the pose of the end effector. And now you are exploring the redundancy of the structure. You have a 7 degree of freedom robot that has to keep the pose, which is a 6-dimensional task, position and orientation, but there is some internal motion that can be achieved, and by pushing on the structure, the controller keeps the end effector at rest in the given position, and you explore what is called the self-motion of this structure. We will see this in details when we attack the first topic related to kinematic redundancy. Okay, so these are examples of joint compliance that affect or that contribute to the motion and which should be controlled. There are other situations, as I said, where you on purpose introduce compliance at the joints, a very large compliance in case, under the condition that you're able to modify online without opening the structure. So you have extra motors that can be commanded in such a way that you perform this type of modification of the joint stiffness. As I mentioned last time, it's like in our body having two agonistic-antagonistic muscles acting on one joint, like our biceps and triceps. And you can use the two commands to move as you desire, but changing on the fly also the stiffness. So why is this important? There are many reasons for this. Initially, this idea was introduced for safety purpose. So we would like to be able, when the speed of the robot increases, and so a potential collision would transfer a lot of energy to the environment or to the human which is being hit. So having soft joints will absorb part of this energy in the collision, so for a safety reason. But people realize later on that it depends on how you control motion and stiffness at the same time. For instance, you can move such structure in the free space and store potential energy inside the structure until you release all of a sudden, in an impulsive way, this potential energy accumulated in the deformation of the joints. And this energy can be used, for instance, for throwing an object very far away, much farther than you would do if you had a stiff joint and the same amount of torque available in your motor. And the factor may be a factor of 10, so a rigid joint can be used to throw a ball, let's say, by 3-4 meters, using in a right way, in an optimal way, a variable stiffness actuation, you can reach 15 meters or so, okay? So this is another use of variable stiffness actuation, so changing on the fly the stiffness. The last use is, in fact, a matter of safety for the robot itself. A very stiff robot performing non-typical action like making a hole with a hammer, where there are impulsive forces acting on the rigid structure, the robot will not sustain impulsive forces of this type if there is no compliance inside the structure. Okay? So not only safety for the human, but also robustness for the mechanical part. So let's see a simple example. This is a quite old movie. Here you see a low-cost unit which has different stiffness, high or low. Now low, you see that you didn't change the structure, you just modify the control of the stiffness in the motors which are inside the cube of this structure, and you can move from low to high stiffness and vice versa. Now the second video is a torso. So it's the upper part of a humanoid made up of several of these cube, which are called cubi move, so variable stiffness actuation connected by some lightweight structure, plastic or whatever, so that you have a left hand, a right hand, and a torso. And playing drums. Does anybody of you play drums? Nobody. Okay. But you may know that expert drummers are able to put in resonance their sticks, so to double the frequency at which they hit the drum without doubling the motion. Okay, they bring the system into resonance in a sense. And of course, if you have a rigid grasping and a rigid structure, in order to double the frequency, you have to move twice as fast. In this case, you can achieve this kind of resonance by the presence of the elasticity. And there are more to be seen in this short video. This is the first type. And this is throwing an object, I mean, just to demonstrate things. And here, having a higher frequency. There was a demo in this institute 5 years ago, and this is the robustness. So you can hit on the structure without hurting it. There was a demo in this department 5 years ago, and it was very fun, if you like music, because this device was able to play the drum of My Sharona, if you know the song. Okay, the neck. It's a very famous song. You can find it on YouTube. If okay, and finally, we have seen the problem of assembly. Now, compliance and variable stiffness compliance can be used. Actuation can be used to perform peg-in-hole task without all the details of the geometry, but just doing some bubbling motion, so trying to find, like you do when you're not able to mount to very tiny parts which have a low level of clearance, so you should be very accurate. You try to move around until you find the right position. It's just an exploratory motion. And this is what happened. It's automatically done by the presence of compliance. So this is a peg-in-hole problem. Now the diameter is 29, the hole is 30, so there's a 1 millimeter of clearance. So one hand you're holding the hole, the other hand you're holding the peg, and now you get in contact, and now you try to do this bubbling until you're able to insert the part. Okay, and now you repeat this by changing parts and reducing the clearance. This is 29.5 peg and 30, so half a millimeter of clearance, so very tight assembly. And again, first you get in contact, then you command this type of vibratory motion. And okay, here it is. And now slowly you can insert this. This is very similar to what you do in practice, okay? And there are other parts, free sliding and so on. I think that this is enough for this aspect. So let's move on to the next one. Okay, so the last set of videos are related to the problem of human-robot interaction. In this case, as I mentioned, safety is really the basic requirement, something that in industrial setting you used to guarantee by putting cages around the robot, so avoiding that the human operator access the workspace of an industrial robot, typically even very large, huge ones, when you have given power to the motor. So the robot can only stay still, or you should use some safety precaution, the presence of a red button on the joystick, on the teaching box, and so on and so on. So now, if you want to collaborate with a robot, if this robot is eventually coming to your home and help elderly people to move around, you have to deal with safety in a different way, not separating the robot from the human. So this is an early video which I've taken during my sabbatical at DLR, so at the Institute of Mechatronics and Robotics of the German Aerospace Agency in Munich, near Munich. I was there for 8 months, and we developed together these techniques. Now you see the blue version of the same robot that you have seen before. It became orange, so this is the DLR-3. It was only a research manipulator. In fact, it was lightweight for a very special reason, because this robot was intended to go in space, in the space shuttle, in fact. And you know that in any space mission, weight costs. Every kilogram is very expensive. So they decided to build a lightweight structure, and then they realized that this lightweight structure was so light that it could not be used on Earth. The motor were too heavy. So they have this idea to design completely from scratch a new robot with very light components, but very efficient. So this is the 7 degrees of freedom robot. It's exactly the same kinematics as the one that we have in the lab. And the robot is commanded here to make some free motion, go from an initial position to a final position and then back and forth. And it would do so if it doesn't hit anything. But in fact, it will hit my arm and will detect this collision without the need of any exteroceptive sensor. So in this video, there's no camera, there's no sensitive skin, no proximity sensor, nothing else than internal encoders, the minimum sensory equipment. So the reason why I'm saying sensorless is not completely without sensor, but with no special sensor for this contact detection. And this is what happens. So the robot stops as soon as he detects the contact and then puts himself in a floating mode, so gravity compensated. So every new collision, it will react by moving. So I can move it around in a very safe way, okay? After we did this experiment, of course, all the students present in the lab wanted to try it out, okay? This was very, very funny. So for this method that we will see toward the end of our course is based on, we call it a residual method. It's based on the full information on the robot dynamic model, on the encoder readings, this is a minimum requirement, and on the knowledge of what torques you're commanding through your controller, so something that you compute, at least when we are assuming that the robot is rigid, okay? So things started in this way. Soon after, in March, a master student whose name is Sami Ad-Din tried it out on itself. So I should warn you, never do this, okay? Never do this. Okay? Let me see if we can see it again. It was very brave. So don't do this unless you're 100% or even 120% sure of your research results, so that you are confident that everything will work as you expect. And in fact, I don't know if I made the right choice. No, okay. Sorry, you cannot see this. But in fact, there's Sami is nowadays, let's say 13 years after, is now leading a huge research center on robotics and intelligent mechatronics in Munich with 120 researchers. So he was a very successful master student. Okay, so the next and last video will be again on human-robot interaction, but we focus here more on the collaboration aspect, and in particular on the capability of controlling force exchanged at any level of the structure of the robot. In particular, we will see that we are able to reproduce an impedance controller like we have seen in the previous experiment on the lightweight robot at the DLR, but now at any level of the structure. So we can impose a mass spring model in a generic contact point on the structure, not necessarily at the level of end effector. So in this video we will start, this was ICRA 2015 video, so the first part is on impedance control at the contact without modifying the natural inertia. And you see that Emanuele is pushing in any point of the structure, in any direction, and achieving a natural reaction of the mass spring damper type. Indeed, we can modify this behavior by imposing more mass or less mass, more stiffness behavior or less stiffness behavior, and you can see that in the various directions the reaction of the robot to the applied force will vary accordingly. The last part will be explicit control of the interaction force. In this case, there are some problems. We will see first an experiment where things go well, and later on we will see something that goes wrong. And the fact that it goes wrong is because there is some missing task compatibility. So now in the direction where Emanuele is pushing the robot, we would like to see 15 Newton applied. So if I push less, the robot will go against the hand. If we push more, the robot will recede. But if we push in a different direction than what expected, the robot escapes because there's no force being applied in the direction which is predicted. So after realizing that we made in fact a mistake here, we discovered that we can only control force in one specific direction, not in a generic direction in the Cartesian space, namely the one in which we are pushing. So the system is identifying the contact, is identifying the direction along which the human is pushing the robot, and in that direction its controller is regulating the contact force at the value which is, in this case, 15 Newton. And at this stage, in the other direction we have no control and we don't need to control anything. In this single direction, which may change according to the type of content and direction of pushing, the robot is being able to regulate force as well. Now, all this material has been developed also inside the European research project that we participated to. First, the FRIENDS project, the collision detection scheme was developed within that research, and later on the SAFARI project is a European project for which our department acted as a European coordinator, and later on the Simplexity project, which was more oriented to application, in particular in which is called Factory of the Future of the European Union, where the concern was on some particular mechanical operation for metallic parts, surface finishing. And finally, some results have been used also within the Comanoid project, but in this case, in an aircraft manufacturing site, Airbus, humanoids were used, so not fixed base manipulator. So these things have been covered by Professor Oriolo in his Autonomous and Mobile Robots course. So, and with this, we complete this introduction, and the next lecture will be devoted to the first technical topic, which is kinematic calibration. Thank you for listening.